Now, one of the things that, so the aperture stop we are interested in because it affects so many different parameters of imaging. So vignetting is one of the things that arises, and let's look at what exactly this is. So in this image, I have an object and a set of rays have been traced, only some rays are being traced through the system. A set of rays are being traced from an on-axis object point, those are the ones in red, and another set of rays are being traced from one of the extremes of the object. And you can see that the angle between this set of rays and the angle over here, this angle, let's call this theta 1 and theta 2, theta 1 is larger than theta 2. Now, these set of rays are not chosen arbitrarily. You have the aperture stop of the system, and so the cone of rays that has been chosen for each point on the object is such that this is the cone that makes it through the aperture stop, which now we know and can say confidently, it means this is the cone of rays that are reaching the image plane, right? But in every case, so in every point if I took on this object, while there is a cone of rays from that point that reaches the image plane, and the aperture stop will tell me now what is that cone. The point to take away from this image is that that cone is different for every object point. It's not the same. The point on the axis gives me the maximum size. So theta 1 is the largest cone of light that will travel from any point on the object to the image. As I go away from the axial point, the cone goes on reducing, and the smallest cone is going to be at the extremity of the object. What does that mean for the image? How is this going to affect the image? Does it make the image blurred? So it doesn't affect the quality of the image in terms of focus, but yes, you're right, it will lower the intensity of the image, and this is an effect that we may see often when we take a photograph, right? So here this is just a photograph of a plane surface so that it's very clear. Actually this should have all been the same color, but you can see the corners are a little darker. And here's a picture taken in the mountains, and again you can see that it's darker in the corners, and this is a typical example of vignetting. Okay, so it's something that happens regularly, it's not unnatural for us to see this. Vignetting could be an issue if you are trying to image, say, some tissue or cell and make some diagnostic based on that image. But artists or people taking photographs for to highlight some point may actually ensure there's vignetting in the system because they want to bring the center of the photograph, you know, they want to highlight that, and they will actually make sure, they will set the camera to enhance the vignetting effect. Or you can even have digital tools where you can say add vignetting to the photograph so that you can highlight the central part of the photograph and dim out the outer region. So it is either something useful or not useful depending upon your application. As I said, people may use vignetting or not. Now how am I changing that? I am changing that by changing the size of the aperture, right? Because clearly if I increase the size of the aperture stop, yes, the central cone is always going to be larger than the cone coming from the edges, but the cone from the edges may be so large that I don't see the difference in the brightness. I might get enough brightness from the edges, right? So basically by changing the diameter of the aperture, I can change the intensity coming into the system. Now in a lab experiment, the aperture shown here is a very typical, you can see this is a very set of thin blades, if you will, and by rotating the screw here you can change the aperture diameter, and these blades will move out or move in, creating different diameters. Okay. You have something similar in a camera where you say you want to change settings, and as we go along in the course, you'll see why you need to do that or the different effects you get from doing that. Okay. So we come now to a very important definition, right? We've seen size of aperture affects some things. We now can define a parameter called the f number. It's written as f number like this, or f sometimes f slash hash, sometimes f subscript hash. Okay, and basically it is a way of telling us, is this aperture large or small? Now, as scientists, you know, when you say large or small, it's always really in relationship to something. Something could be very large in relationship to another parameter. You might be saying 100 nanometers is large. It depends on what you're comparing it to. Right. So here, when we talk about the f number, we are talking about whether an aperture is small or large, and we do that in terms of the focal length of the lens, right? So we had this concept earlier when we said, is it a thin lens or is it a thick lens? Said, what are the object and image distances compared to the focal length of the lens, for example. So the f number is defined as the focal length divided by the diameter of the lens. This actually is a definition really used for infinite conjugates, but very often in photography it will be used even if your object is closer to the lens and not really at infinity. We won't go into the working f number definition, which is the definition you use for objects that are closer, but to understand the importance of the f number, it's enough to just take this definition with infinite conjugates. Now, this is also called the speed of the lens, okay, and we'll see why it's called the speed of the lens. So we know now that aperture size changes the intensity reaching the image, at least at different points. It also controls something called depth of field and focus, and we're going to see that it is also going to play a major role in the aberrations in the system. In other words, the quality of the image. Okay. So why do we say the f number is related to speed of the lens? Well, if I'm changing the diameter, and this image here shows typical camera settings. If you will see on a camera, that you've already told me none of you are photographers apart from cell phone camera, so you're not going to see these numbers on a cell phone camera. But if you take what was earlier the standard camera, you will find that on the lens you would have these numbers, and you could change a setting, and that would change this f number of your lens from either f2 to f16. These are standard numbers. Okay. Now you can clearly see that the higher f number, f16, has a very small diameter, right? Where exactly do these numbers arise from? Well, they arise from the fact that every time you double the diameter, you're doubling, so you can say that it's a circle, so I have an area of pi r squared. Now every time you double the diameter, you're actually increasing the area fourfold. That means the amount of light that's coming in is 4 times more. And that's where the speed of the lens starts coming into play, because with all of these systems you're doing imaging. So you say a certain amount of light is coming in, and then there has to be an exposure. Earlier you were exposing a photographic film. Nowadays, of course, we don't do that, but even there the digital sensor needs to have the light incident on it for a certain amount of time for it to capture a good image. Okay. How much time depends on how much light. You have a low lit situation or object being imaged, you need a longer exposure time, and vice versa. Now, it's not just how much light, what is the ambient lighting, it is also the setting of the camera, right? If you say auto set, the camera will sense, there's a sensor which says there's so much light present, because there's so much light, we will choose this setting. There's a lot of ambient light, so we will use the smallest diameter. However, if the setting has very low light, it may choose a much larger diameter, right? You can force the camera to have a certain diameter. Depending then on the lighting, it will choose the exposure time. So, say the lighting is very low and yet you choose f/16. So, the diameter is also very small. The camera will then take a longer time to expose or to capture the image. Now, for photographers, that means several things. Normally, you want to take a photograph before the handshake changes the position of the camera. So, you want the camera, the exposure time to be in the odd less than 1 second, 1/250th of a second, let us say. Okay. If you take it at that speed, so the shutter of the camera opens and closes in 1/250th of a second, that image will be captured before your hands have moved. There's always some movement, right? But if I force the camera in a low light situation to have a small aperture like this, it may take several seconds to take an image, and if I am taking the image holding the camera will move around and you can get some funky effects where you see streaks of light, right? Otherwise, you have to put the camera on a tripod so that it doesn't move during the exposure. Okay? So, people exploit these. Say you're taking a picture of some stars moving, right? You want to keep it open for a very long period of time and it is taking a picture continuously as there's a movement of the stars, and you will see that track as the stars are moving, right? So, it depends again on your situation, but we call it speed of the lens because clearly a faster lens is a lens with a larger diameter where the aperture is larger. This is a faster lens, right? So, the faster lens has the smaller f numbers, keep that in mind. Okay. Now, you can see doubling the radius makes the light intensity go up by 4 times. So, the camera settings are such that every time you go up one stop, so f2 to f2.8, where do these numbers come from? You are actually saying let's change the area such that the exposure time doubles, right? Not goes up. So, I am not changing, I am not going, this radius is not half of this radius. This radius has been changed such that the area has only gone up the area has gone down 2 times, right? So, if I am going from f16 to f2, the area of this has doubled compared to the area of this. The area of f8 has doubled compared to f11, and that means you keep going down in exposure time by half. Okay, and that's where these numbers come by. It's, you're not doing the area by 4 times but by 2 times. Okay. So, of course, the exposure time is going to be really large for f/16 compared to f/2. Okay. Okay. So, it should be pretty clear that changing aperture is relating to exposure time, right? Okay. Okay. But that's again not the only thing that the aperture size affects, right? So, here let's look at this image. I have a lens and I have an aperture. So, maybe this is the mount of the lens, maybe this is what is holding the lens and it is acting as the aperture stop of the system. So, I have a beam that is incident, and this beam is the largest size beam that makes it through the system. Now, the ideal focus is this plane here called the paraxial focal plane. You can see that this beam is focused to this point over here. If I go a slight difference or distance away, let's say I defocus. So, instead of putting my image plane here, I go delta distance away. Now, you can see that instead of having a point focus, the beam has diverged. So, the focus now has this size. There is now a finite spot size, right? It may be that this blur, this is what is blur, but it may be that this blur is still acceptable. My eye will not see this as blur. It's larger than a point, but it's smaller than what starts impacting my vision, right? So if I went further, let's say I went to this plane. Here I have a point, here I have this size, and now here I have this size. This may be totally unacceptable. That means I have everywhere in my image, instead of having sharp points in focus, I have a blur circle everywhere. Clearly it's a completely blurred image, right? So for this particular system with this aperture stop, maybe this is an allowed displacement. So we call that the depth of focus. I can move so much distance away from the ideal, the paraxial focus plane, and of course if I can move this much on this side, I can move an equal distance on this side, because that's the distance, the blur on the other side. So there's that much distance I can displace the focal plane and still say the image is acceptable. We call that the allowed depth of focus. So it's how much. So this isn't going to happen in a camera, or actually you could think of, this is the distance the camera manufacturer, this is the error he is allowed in placing the CCD sensor into the camera. It ought to be at the paraxial focal plane, but if there's an error in his manufacturing system that doesn't place it exactly there, but places it anything at the most plus minus delta away from this point, or less than plus minus delta away from this point, then he will still be able to sell this camera because the images will be acceptable. Okay, so this is the tolerance that is allowed. I can see that if I changed the aperture stop dimension, let's say the aperture ended here, right? That means this much beam of light is coming in, right? It's still the same lens, so it's still focusing at the same place. But you can see what was just a blur of this size over here has now become a blur of this size for the same lens, but for a different aperture stop. Now this lens, this delta is no longer an acceptable depth of focus. The image is blurred even having moved the same distance away from the paraxial image plane. What changed that? The size of the aperture stop. And you could take this argument a step further and say, well, if I had not increased the size of the aperture stop, but I had decreased it, then I would be able to have a larger, maybe 2 delta I could go. So I would have a larger depth of focus. So the depth of focus is related to the diameter of the aperture stop. And one of the very first cameras was a pinhole camera, right? Have you heard of the pinhole camera? No lenses. All you had was a pinhole. What is the depth of focus of a pinhole camera? It should have a very large depth of focus because the aperture stop is this pinhole, this very small hole. So it actually has an infinite depth of focus. It has really only paraxial rays coming in, right? So a pinhole camera has an infinite depth of focus. And I'll put focus, right? But what's the downside of a pinhole camera? Yes, it has an infinite depth of focus, but does that mean it's wonderful? Let's all use a pinhole camera. What's the downside of the pinhole camera? It allows very less light. So it also, you could almost say, has an infinite exposure time. Well, it's not really infinite, but you need a long exposure time in order to capture an image with a pinhole camera, because of course the amount of light coming through is very, very low. Okay, so there's always a trade-off, there's always a compromise. Maybe you're taking a photograph of a waterfall. You want to capture the moment So you want to make it look like the water was frozen in time, right? You then, and you want the mountain or the rock behind it to be blurred, right? Then you want to very quickly capture, so you want a fast lens, right? The fast lens means it has a large aperture, it captures very quickly, so the rock, or if there's something moving behind, that's not going to be seen, only this water is frozen in time. On the other hand, I could have a long exposure, and then you're actually taking the picture over a long time. It will look like the water will blur out, because that scene is changing. It's changing as the image is being taken, right? So again, depending on your application, I'm giving the example here of photographs, but it could also be, are you viewing a sample and the sample has live cells or some live bacteria, and you want to capture the bacteria frozen in position, or you want to see how they move, and that will change the setting of your system. Okay. So aperture stop affects depth of focus, but I also have depth of field. Now, what is depth of field? I said, and I showed in the previous image, that for a particular optical system, you have the paraxial focal plane, and the depth of focus allowed you to move a little bit away from that plane and still have an acceptable image. I can say, how much can I move away from my perfect object plane and still have an acceptable image? So again, I have an object lens, I have an object, and I have the perfect image plane. This is my paraxial image plane. Right? Now, let's say this object is not exactly a plane. We are not always photographing two-dimensional things, right? Let's say the object is like this. Does that mean only one part of that object is in focus and everything else is blurred? Of course not, right? There is some distance here that I'm capturing it on one plane, but all of this should come as in focus, right? So the variation allowed here, variation in object distance, this is the depth of field. Okay. And just the same argument we used with the aperture stop and the depth of focus, that's exactly what I'll use over here. Right. So again, aperture stop is controlling depth of field as well. Okay. Okay, so I have some images here to emphasize what we are saying. Here's a photograph that's taken of a billiard table, at sort of at glancing angle, and you can see it's been taken, you've been told it's been taken with f number of 2.8. In the image, the billiard ball in the front is clearly sharply focused and the ones behind are blurred. Okay, so it's you could say this was taken with the camera set to have a very shallow depth of field. This is the entire object that I want to image, is this entire billiards table. You can stop down the camera setting, so you've gone now to f number 16, and now the whole field is in focus, right? But clearly whoever took this photograph had to take this one with the longer exposure time, because now the amount of light coming in was less, right? Again, in movies, people use this technique. So if two people are talking, they bring you, how do they direct your focus to something? They will have the camera set to a shallow depth of field. So the background is blurred and only one thing or one person is in focus. So naturally you tend to look there. And then they want to shift your focus somewhere else. They either change the focal position and they still have a shallow depth of field, but they've changed the entire focal setting so that the shallow depth of focus is now shifted to somewhere behind, or they change the setting so that everything becomes in focus, right? So you can play around with depth of field, depth of focus simply by changing the aperture stop dimensions, right? And you should be able to extend this idea to aberrations, because what are aberrations? We are using optics to design an imaging system, and you want the image to be crystal clear and sharp, no blur. We know we are not using the perfect or the correct lenses for that. The correct lenses should have a Cartesian oval shape. We are using spherical shaped lenses, and we are saying as long as the rays are paraxial, they work pretty good. All the rays from any point have the same optical path length. But that's not really the case, and many times the rays we are using are not exactly paraxial. We are going to have blur in the system. We are going to have our lenses are a function of refractive index. Refractive index is different for different wavelengths. So you can have aberrations in your image because the wavelength of your light source is not a single wavelength. You can have aberrations in your image because your rays are not paraxial. But you should be able to now get the idea, the aperture stop limits rays traveling through the system, and by controlling which rays travel through the system, I should be able to improve the quality of my image, because some rays will definitely make the image worse, and if I cut them out, I'll improve my image. Okay, and that we'll see over the next few classes what are aberrations and how using an aperture stop would actually help us. Okay, I think. Yeah, so I just have this, it's basically a summary of what I said. If you have these different aperture settings and this was your object, which of these would you say has been imaged by, let's say the upper image was created using the f/2 setting or the f/16 setting? So the top one is the f/16, right? Because it has a large depth of field, right? And maybe this was created by this with a very shallow depth of field.